In this module, we'll consider problems when we have more than one object. We will begin with the example of two boxes on a horizontal surface. We will have a force with a magnitude F that acts on a box with a mass m, which is in contact with a larger box that has a mass 3 times as large, or 3m. Both boxes are sliding to the right along a horizontal surface with a coefficient of kinetic friction between the boxes and the surface equal to mu. Determine the acceleration of the boxes and the force with which they interact with each other. Many students are confused and inexperienced in solving problems in symbols. So what do we expect to get in our answer when nobody has given us any numeric values? What you usually do is go through the problem and underscore every symbol that is given in the problem, and that symbol is allowed to appear in our answer. We have here a magnitude F for the force, so F, we can actually get F in our answer. We also have the symbol M for the masses of the two boxes, one being M and the other one being 3M, so we can actually keep M in our answer. And we have one more thing here, the coefficient of kinetic friction, mu. So our answer can contain F, M, and mu. And in addition to that, we can also have some numeric factors, 3 or 4 or whatever comes out. We can have the gravitational constant G or other mathematical or physical constants. So with that, let's see what we have. Here's the horizontal surface with the two boxes M and 3M and the force F acting in a horizontal direction directly upon the box with the mass M. We will start with analyzing the motion of the box with mass M. We're going to pull it away from the picture, and we're going to draw all the forces acting on it. And remember, when we do that, we talk about the free body diagram. I will have the vector F that the problem tells me it applies to this small box with mass M. Of course, I'll have gravity pointing downwards and the normal force pointing upwards. I will have friction pointing to the left, opposing the sliding. Presumably the sliding is to the right, as the problem says. And I will have to add one more vector that points to the left to account for the interaction between the two boxes M and 3M. And there we have our free body diagram for the box with the mass M. I will set up my coordinate system with X to the right and Y to the top, and with that I'll go around and add the components of each of those vectors that I have on my free body diagram. For the gravitational force, I'll have 0 and minus mg. For the normal force, I will have 0 and plus Fn. Remember, Fn here stands for the vertical component of the normal force. For the pushing force F, I will write it as plus F and 0 to account for the fact that the force is actually directly in the horizontal direction, pointing in the positive direction of X. And for the friction, I will have minus mu Fn and 0. Minus because friction points to the left, and mu Fn because I know that the magnitude of the friction is always a fraction of the magnitude of the normal force. What that fraction is determined by the coefficient of friction between the surfaces that are sliding. And finally, I will have the components of the force that stands for the interaction between the two boxes, and I will mark those components as minus FB and 0. It is minus because the interaction here appears to be a push to the left for the small box M. We'll see that the interaction will appear as a push to the right for the bigger box on the second diagram. So we're ready to write the equations here for the box with the mass little m based on Newton's second law. Remember, we're going to work in components, so we're going to start with the x components. I will go around all the vectors and I will add all the x components. The gravity and normal force will have no x component, so I'm going to jump directly to the friction with an x component of minus mu Fn, and plus F, that's the x component of the pushing force, and minus Fb, that's the x component of the force that emerges from the interaction between the two boxes. That has to be equal to m times the x component of the acceleration of this box M. For the y components, First, I'm going to note that I will have no y component in the acceleration, so I'm going to set up the right-hand side here equal to 0. Remember, there are no changes in the motion along the vertical direction of the boxes. They're just sliding along the horizontal direction, but nothing is changing along the vertical direction. Because of that, my equation will be minus mg for the y component of the gravitational force, plus Fn for the y component of the normal force. The remaining three vectors have 0 for y component, so that has to be equal to 0. So the y component relationship gives me a very simple equation that tells me that the normal force Fn will have to be equal to numerically to the product between the mass m and g. And of course, the frictional force then will be mu Fn or mu mg. With that expression, I can go and put it back into the first equation that I got from the x components. And so it will look like that. Minus mu times the Fn, which will be mg, plus F minus Fb has to be equal to m times the x component of the acceleration of this box m. So here is my first equation emerging from the dynamics analysis of the box M. I still have two unknowns, the force with which the two boxes interact and the x component of the acceleration of the box M. So I need to do more to get at least one more equation. And that second equation will come from the free body diagram for the box with mass 3m. Here's my larger box 3m with the coordinate system x and y, the gravitational force pointing downwards with components 0 and minus 3mg. Notice because the mass here is 3m, the gravitational force will have for its y component a larger value. The same can be said about the normal force, but I will mark it as Fn here, so I'm going to have 0 and Fn. For the frictional force, it is going to be minus mu Fn and 0 for the y component. And I will have to add one more vector here to account for the interaction between the two boxes. Remember, the interaction is one between the walls of those two boxes. On the small box, that interaction shows up as a push to the left, but on the big box, the box on the right, 3m, that interaction will show up as a push to the right. So this is why the component here of the vector, the x component for this vector, is going to be positive, but I will keep the same symbol Fb because in terms of the magnitude, this vector has the same magnitude as the vector for that force on the free body diagram for the smaller box. Here is where many students make a mistake initially when they're not experienced with this type of problems, and they like to draw one extra vector F for the force that is pushing the two boxes to the right. But it is not correct, and the reason is because on the free body diagrams we draw vectors that apply directly to that object. So except for the gravity, which is the only force that acts over distance, all the other vectors actually stand for an interaction that emerges from a physical direct contact. We have a contact between the bottom of the box and the surface, so that is why I drew two vectors, for the normal force and for the friction. And I also have one physical interaction between the small and the large box, and that is why I have that force Fb. But the original force that pushes the small box m does not touch the large box 3m, so it does not belong to the free body diagram for the large box. Now let's write the equations for this large box based on Newton's second law. For the x components, I'm going to have minus mu Fn, that's the x component of the frictional force, plus Fb, the x component of the force between the two boxes, and that has to be equal to 3 times the mass, 3m, times the x component of the acceleration of that box. For the y components, I will have minus 3mg for the gravitational component plus Fn, that's for the normal force, has to be equal to 0. Again, remember, we have no y component of the acceleration. In other words, what this means is that there are no changes in its motion in the vertical direction. It stays on the table and remains to stay in the table even though it's sliding left and right. So the second equation here gives me the value, how much is actually the normal force, or its y component. Fn will be equal to 3mg. And so once I know that, I can go back to the equation for x and replace the normal force with its value, so that my equation here for the x becomes minus mu times the Fn, but now I'm going to write it as 3mg, plus Fb is equal to 3m times the x component of the acceleration. And there it is, my second equation that will allow me to solve for the problem and find the answers. Remember, we're looking for the acceleration of the boxes and the force with which they interact with each other. I will need a little bit more space, so let me clear up some space here. In the middle, I have circled my two equations. What is left here is to do some algebra. My two unknowns here are the force Fb, or actually the component, the symbol Fb that stands for the magnitude of the force with which the two boxes interact, and the x component of the acceleration of the boxes. In fact, that x component for the acceleration is the same for both boxes because they move as one. So as long as they move as one object, I can say that both the x component for the box M is this, for the acceleration of the box M, is the same as the x component for the acceleration of the box 3m. I don't need to worry about Fb. Of course, I have Newton's third law that ensures that the force between the two boxes is always the same for both boxes. The only thing different here is the direction. So with that, we're ready to do the algebra. I will take the left-hand side of the top equation, minus mu mg plus f minus fb, and I will add to it the left-hand side of the second equation, minus mu 3mg. I shuffled the order of the symbols here, so I wrote it here as minus 3 mu mg plus fb. I will set up equal, and on the right-hand side, I'm going to add the right-hand side from the first equation to the right-hand side of the second equation. Opening the parentheses and simplifying, we'll see that we have minus mu mg plus f minus fb minus 3 mu mg plus fb has to be equal to 4max. I can cancel here fb, that component of the force between the boxes, and combine the mu mg terms so that I get minus 4 mu mg plus f, the pushing force, has to be equal to 4m, the x component of the acceleration of the boxes, and that gives me the answer for the acceleration of the boxes. The x component is going to be equal to f minus 4 mu mg divided by 4m. Remember, the y component is 0, so this answer is going to be the answer for the magnitude of the acceleration of the boxes. What remains here is to answer what will be the force with which they interact with each other. So I can take the value here for the acceleration, or for the x component of the acceleration, and put it in one of those equations that emerge from Newton's second law. In this case, I chose to use the second equation. So wherever I have ax, I'm going to replace it with the expression of f minus 4 mu mg divided by 4m. Let's see how this equation is going to look. I'm going to have minus mu 3mg plus fb, and that has to be equal to 3m times the x component of the acceleration, which I know is equal to f minus 4 mu mg divided by 4m. And here's some fun. M here on the right-hand side of this equation will cancel, and I can distribute it actually. So what I can do here is to move the term minus mu times 3mg to the right and see that the force with which the two boxes interact, Fb, will be equal to plus 3 mu mg. Again, I shuffled the order here of my symbols. Plus, I distributed here the factor of 3/4, so I'm going to have 3/4 of F minus 3/4 of 4 mu mg. So once again, another cancellation here of a factor of 4 in the last term here on the right. But even more so, the entire term cancels out, because if you think about it, its value turns out to be minus 3 mu mg, which, and we already have one term that says plus 3 mu mg. Finally, we can write for the force between the two boxes that it's going to be equal to 3/4 of the magnitude of the force F with which the small box is being pushed. I like to work problems in symbols, and you can see why. The reason is that we can see a pattern in the end. If we had the numeric values of the F and M and mu, would have been working with the numeric values and would have missed the fact that the answer for the force between the boxes depends only on the ratio between the masses of the two boxes, or the fact that one is m and the other one is 3m, but it does not depend on anything else. So here's our answer.